Welcome to Queens College Physics Department's distance lab program. This is Lab 6, Friction. The resources for this lab are the file you're seeing in the video and the video of itself, which you're now watching. There's also a capstone file which contains the raw data from which you're going to extract some information. For your report, for the abstract, briefly discuss how important friction is in the real world. Particularly in industry, friction is much bigger than many people realize. It never gets discussed, but it's still a subject of active research. The operative word here is briefly. Do not spend a lot of time doing this. Just show us you care. Equipment. The equipment is the tracks and carts that we've used before. That's not new. What is new is the way we measure mass. In the earlier labs, we used a digital scale, the uncertainty for which is quite simple to understand. However, this lab works best with larger amounts of mass, and I'm going to be using from roughly 400 grams to 2 kilograms, and that cannot be measured on one of those digital scales. We're going to have to use a balance, and that requires some discussion that we haven't had before. You'll see that a little later in the video. The data for procedure 1, you'll have a table and a plot, and for procedure 2, you'll have a screenshot of capstone. The same for procedure 3. The analysis and conclusions is embedded in the description of the procedures. You can read the introduction on your own time. It won't be any different than what you've learned in class or can find at any place in the web. So let's look at the equipment. I'm going to switch to the video camera now. And here we are. This is the equipment that we'll be using from the lab. You can see the balance here. It should, if I do this, the important part about a balance is that it be balanced. We'll talk about that more in a minute. With a balance, you need a calibrated set of masses. In this case, we're using so much mass that I actually need to borrow some from a second set. For the friction, we're going to be using a friction cart, which is simply a plastic cart. The important part is it's got a cork bottom and a place to hold mass. This is the mass we're going to use. The black ones are 500 grams. The gray ones are 250 grams. Of course, each of those has their own uncertainty, and rather than try and calculate that uncertainty, we're simply going to measure the entire cart each time. The smart cart in the first procedure is simply used to as a force sensor. There's a force sensor built into the front, and we're going to directly measure the force of friction. In a later one, we're going to use the wheels for the rotary encoder to measure the position of the cart as it decelerates due to friction. We'll get to those when we're discussing the project. Level, because the track must be level. Why must the track be level? Because we want the normal force to be mg with no cosine theta factors. And that only happens if the track is perpendicular. And that's it. Okay, let's take a look at how to use a balance. The first thing you must do is set everything to 0, nothing on either pan. This is set to 0, and you should look at the pin here. It should be aligned with that little black line in the back. That means it's balanced. Why do we use a balance? Because we're comparing masses, and in both cases, while the force of gravity, the weight, is holding it down, mg on both sides, the G cancels. So we're comparing directly the masses. We're going to put our the mass we want to measure, and in this case I'm going to do the maximum, which is 1, 2, a little over 2 kilograms. And I'm going to put them here. The unknown mass, the part you're going to measure, always goes on the left-hand balance pan. Now we need to put masses here in order to balance this. And then we'll do the fine adjustment with this bar here. I'm going to leave it in the middle just because that's the way I like to do things. I'm going to take from the calibrated sets. I have 2 calibrated sets because I need so much mass. I have 500, not enough. And then I'm going to take 2 for 500 more, still not enough. And I'm going to take another 500, still not enough. I'm going to take 2 for 500 more, still not enough. I add 50, need more, and 20 is 70, and 20 is 90, and there. So that's 2100, right? 50, 60, that's 2100. And now I'm going to use the beam and adjust it so that it's back in balance. Let's take a second. And there we go. If we read the balance, the numbers are grams. The divisions between are 1/10 of a gram. And of course, when we're reading something like this, we'll guesstimate a position between 2 marks, and that will be our uncertainty at 1/100th of a gram. So if I read this scale, I have 2100 grams here, and I have 2.14 grams there. And I simply add it all up. So 2100, 2.04 grams. Of course, we're going to be working in kilograms, so it's going to be 2.1024. Was that right? I think that was right. Kilograms. Now, the question of the uncertainty of this. Is it reasonable to think that we can measure this thing to within 1/100th of a gram? Doesn't the uncertainty in a direct measurement like this grow with the size of the thing being measured? If you recall from earlier labs, that sounds correct and is correct. So that uncertainty that we're reading is almost certainly an overestimate, wishful thinking. So let's look for the problems. One problem is how well we line up those marks. And an angle like that is actually going to have very little effect on the balance. It's going to have some, but not very much. We're, of course, estimating a digit here, but again, to the 100th of a gram. But what about this? We just added the number stamped on each of these masses in order to find the total mass. We just added them up. Can they be exactly 500 grams? Clearly not. Each of these must have their own uncertainty. And in the normal course of things, you could be asked to find the uncertainty of that. which means doing a calculation of uncertainty with 3, 6, 9, a dozen objects in it. That's horrendously hard. Not hard, it's just tedious. Is there a simpler way? And the answer is yes. These are calibrated sets. They are precise within 0.1%. So we can, instead of trying to figure out all of the uncertainties of each of these individual masses, we can just look at this mass, the mass we read here, and calculate the uncertainty at 0.1%. So I'm going to show you that in a second. Why am I doing that for the maximum mass that I can use here? Because in the end, that's going to be the uncertainty we want to use. Okay, let me get a piece of paper and show you the next step. Okay, I have a little whiteboard set up here. Let's talk about our measurements of mass. So when we measured the mass with all those calibrated ones, we came up with 2,100 grams. And on the beam, we had 2.14 grams, and if we add them up, it's 2,102.14 grams. We're of course interested only in kilograms, so 2.10214 kilograms. And we are still facing the same question. Is it reasonable to think that we can get that much precision out of this balance? And the answer is no. Because each of those individual weight sizes have their own uncertainty, we have to take that into account, and it adds up. As I said, they're calibrated to plus or minus 0.1%. So this is about relative uncertainty as opposed to absolute uncertainty. And here we're going to take our measurement, take 1% of that, and that's what our uncertainty is going to be. So 0.1% is 0.001, which means we have to move the decimal point 3 times. So we're going to be 0.002, and then we're going to round it to their kilograms. And that's going to be our uncertainty, plus or minus. So that also is going to reflect on our measurement, because we have all of these decimal places. If it's uncertain in this decimal place, then these decimal places are useless to us. So we're going to truncate it to 2.102 kilograms plus or minus 0.002 kilograms. And that's the uncertainty of that measurement. And because that's the maximum uncertainty that we're going to see in our labs, that's the uncertainty of the mass that we're going to use all through the lab. Okay, before we can actually collect data, we need a file to collect it into. I'll open a Capstone file. And I've already turned on the cart. So if I open the hardware setup, the cart appears, trying to pair. I click on that. It says connecting to smart cart. And gives a code that's on the cart. There it's connected, battery's good, all the sensors are on. We're really only interested in the force sensor. And there we go. So I'm going to use a graph. And I'm going to select the measurement that I want to record to force. It automatically sets the x-axis to time, which is the most convenient. If I now just hit record, it starts to record. I want to switch this to the force sensor, and I want to bring the sample rate, how many times a second it reads the force meter, to, let's say, 200. And when I record, I'll hit 0 to make sure it's 0. I'll delete the last run so I have a fresh start. And now, before we start, let me demonstrate what I'm going to be doing on the track. Here we have the track. I have a cloth, and I'm going to wipe down. I already have wiped down the cart and the bottom of the cork bottom cart. I've placed 250 grams in the cart, and I've got a hook that's holding the cart just like that. So I'm going to leave it like this so there's no force on the hook, so I can zero it. Then I'm going to come back here, and while it's recording, I'm going to slowly increase the mass until it moves. So that's increasing. We're increasing the friction force, the static friction force, which is what we're measuring directly here, until it moves. And when it moves, that's what we're going to take as the maximum static friction, from which we can calculate mu. Okay, so let me set it up for a run. Okay, so I'm ready now. You can see on the inset how it progresses in the capstone file. I press record and 0, and now I come over to the cart and I start to build up force until it moves, stop, release it, build up force until it moves, stop, release it, build up force, stop, release it, build up force until it moves, stop, release it, and I'm going to do that 6 times. And that's it. So now I can stop the recording. And here we have our data. Didn't look like much in the inset because the scale was jacked way up, but now you can see what it is. The first shot is always a little bit hairy. And often I've found when I was doing this that it was out of scale to the rest as well. We are going to just eliminate that from our considerations and only take the next 5. Now I can't do 10 and just pick the best ones because that's us imposing our expectations on the data. But I can set a rule. We will always ignore the first one. We will always take the next 5. And that's it. So how do we get the data? What data do you want to extract from this? Well, we want to know the peak value because that's going to be the maximum static friction. How do we do this? Well, I'm going to use the mean of something. What? Well, I can do this. And I get a mean value, but it's the mean value of a bunch of stuff, and I'm not quite sure what's going on here. I'm not happy with that completely. The other thing I can do is actually do a maximum. Now the maximum of everything is not going to help me, but what I can do is now take one of these and make it smaller, and I can do the maximum here. 122, 121, 118, 122, 122. This is all quite similar, so but you'll find in the data that you're going to download that some of the runs have more variation. The problem is that if I scroll in, what am I getting the maximum of? There's, certain oddness going in here that's a part of the data collection system. And I want to avoid that. So I'm going to take this. But I'm going to go back to the mean. And now I'm going to do the same thing. I'm going to bring this down until a mean appears. There it is. 1.21. That's going to be the mean. That's actually more points than I want. There. A mean of 1.21. That's going to be adequate for our purposes. So we're not taking any oddness out of the data. We're getting a average value of the peak. And then we're going to do the same thing here, and here, and here, and here. You'll record those 5 in Excel, and then I'm going to show you how to take the average of them. Now, I'm going to do this. In this one I only have 1 run, but if you do this, you see where it says run. When you open yours up, you're going to find 8 runs that are labeled procedure 1, mass 2, blah, blah, blah. The masses will appear in the Google document, and it will be a similar data point, but each time it will be a higher force because there'll be more mass in them. I'm going to go up by 250 grams for each run. You'll start at 250 plus the cart. You will end up at 2100 and something. Then I'll show you what to do with it in Excel. So that's next. Let's go to Excel. And here I am in an Excel. You're going to prepare your data here for procedure 1. You'll set up a table and you'll plot it. To do the average, I'm going to set up the headers first. F1 tab, F2 tab, F3 tab, F4 tab, F5. And that's going to be the different values that you're going to read in Capstone, which you'll enter in the columns. Here I'm going to do F average. So let's, what was it, 1.21 tab, 1.22 tab, 1.18 tab, 1.21 tab, 1.22 tab. So those are the values that we found in the first one. They're my first one. The ones you download will be different. And now I want to do the average of those. So I click here and I hit equal to tell Excel that I want to do a calculation. The calculation I want to do, and I'm going to type in AVG. Just AV. There we go. And the second one down is average. I double click it, and now I select these and I hit enter. And that's my average. Well, my average should not exceed the number of decimal places here, so let me reduce it by 1. There we go. That's my average force for those 5 peaks. Now, the mass for this, 345.345. So my mass for this run is 0.345 kilograms. I, of course, don't want the mass. I want the normal. And the normal is going to be a calculation equals to tell Excel I want to make a calculation. I click here because this is one of the operands, and I want to multiply it by G, because the normal force is mg in this case. And G we're going to use 9.802. Now this of course has an uncertainty, but the uncertainty is so small here that we can safely ignore it. It's in the 4th decimal place. Everything else we're doing is only 2 decimal places. Easily we can ignore the uncertainty of our G and treat it as an integer value. And I hit enter. And again, that's way too many decimal places. You'll work it out what it should be when you're working on it. But I've got an N of 3.38. You're going to do this 8 times, and you can do the calculations. You can just drag them down. Right now it says divide by 0 or 0, but when you fill in these numbers, it will give you the correct values. And then you're going to plot them. So I see a fair number of people using odd stuffs, but insert scatter plot, and you'll sometimes see people picking lines and stuff like this. We don't do that here. We want this. Now, if there's multiple columns, Excel gets confused and it won't even try to tell you what it should look like. So you right-click and select Data. You add a data series. In the first one, the series name, you type whatever you want to call it. This is going to be F versus N. And here we want the X values. Well, the X values are going to be the normals, and the Y values are going to be the average forces. And then we're going to say OK a bunch of times. Now, that doesn't look like anything here because I haven't written any data. But when you do it, you'll see a set of data points. You'll then right-click, and you don't see it here because there's no data here. Oh, wait, I can use this for data, can I? You're going to have a series of data points. You'll right-click on the graph. You will add a trend line, which is what Excel calls a linear regression. And you'll follow the analysis in the Google Doc. And that's what you're going to do for Procedure 1. Now let's look at Procedure 2. Okay, I'm ready to do Procedure 2. You're going to see a run that will say Procedure 2. It's on a second page where the measurement that we're recording is the position of the cart. And other than that, it's exactly the same. So let's now look at what's happening on the track. Okay, here's my setup on the track. I have a barrier and I have a cart. I've taken out the mass. It's still the same cork on the same track. I'm going to compress this spring. I don't actually care what the value of the spring is. I just need something to launch it effectively. And in this case, when I hit that little black button here, it's going to launch the cart, and it's going to slow down, decelerate, negative acceleration due to the friction generated by the cart. That's going to look like this. And that went right off the screen, almost, but that's okay. Okay, let's look at a data run. I hit record and zero it and release the spring. Off it goes, it slows down and stops, and we're done with recording. All right, let me get rid of the track and go back to Capstone. Here we are. So this is the data I recorded. Mean is no longer useful here. Let me bring this down to something that's going to be more recognizable. There, you should recognize that curve. Now in the Google document, it tells you to only select points that are part of the deceleration, the negative acceleration of the cart slowing down. So here, this first part is probably where the spring is still engaged. So we should ignore it. And if I get a box, let me actually draw the box. I'll start with that point. And I'll come up here, and I want to pick the first point where this flattens out. I'm going to go there. Now, you're going to actually go to the fit menu and pick a fit. Now, it's clearly not linear, and as I said, you should recognize this figure. It's a position diagram for motion diagrams, and you should be able to work out what the acceleration is from this if you follow the analysis in the Google Doc. And that's procedure 2. Let me set up for procedure 3. Okay, I have it set up for procedure 3. Procedure 3, we're going to do an alternative, less precise way of finding the kinetic friction. If I move this until the, let me actually put some mass in here to make it a little easier. Okay, if I move this until it just starts to move, then the force will drop to the kinetic friction. And if I then continue to move it at a constant velocity, then that should be the measurement of the friction force for kinetic friction. Let's set it up to do a run. I hit record, and I zero it, and here we go. I gently pull until it starts to move, and then I keep moving at a constant velocity. Now I don't have anywhere to measure this, I'm just going by eye that I've had the velocity constant. That should be enough. And I hit stop. So this is a little bit noisy, but it's better there. So you see, here's where the friction, static friction builds, hits maximum, drops to kinetic friction. And this is flat, so I should be able to take a mean . Why can't I get the mean? No, it's off. So, and I should be able to take the mean of this. And you can then calculate mu kinetic from this and see if it compares to your value from procedure 2. And that's all I have to show you here. You'll see the data that I've selected for you in the capstone file that you download. The instructions for the analysis are all in the Google Doc. As well as the masses for each of the runs that I did. And I think that's it. So good luck on this week's lab.